All right, welcome everybody. So good to see you here. And we're going to be talking about kitchen tools and equipment. Um, just a couple of notes. So one is that due dates in this class are very flexible. I never mark anybody down for turning in anything late. In my experience, good learning happens if you understand what I'm going to lecture on, right? So rather than just coming at it cold, if you had done some studying, then when I talk, maybe what I say will make more sense, or what you read will make more sense. Well, it'll reinforce it. So the due dates are designed so that the module is due the day of the lecture, which is very different from traditional school where you go in, the teacher lectures, you go home and do the homework. I've never found that to be a very good learning technique. So I have designed this class so that the due dates are the same day as the lecture. So you've looked at the material. You may not turn it in then, but you've looked at it. So that's just my thought. Um, Ryan and I were talking about a question from the quiz. This one here. Let's see if we can. This one right here. So my question read, inductive heating process similar to induction cooktops, which is already a stupid start, right? Induction doesn't mean anything, right? Uses which of the following principles? Well, what I was reading, what I did was from the culinology text, and I tried to reword the words. And this is in the ohmic heating section on page 390 in the textbook. And the textbook reads, the inductive heating process, similar to induction cooktops, uses electromagnetic currents of oscillating electromagnetic fields generated by electric coils in the vicinity of food. So, and that was under the ohmic heating section. So I'm not even sure what they said makes a whole lot of sense, but definitely what I said did not. So, I think what we can learn from this is that they're very similar, right? The difference being that induction heating heats the metal in the bottom of the pan, which then heats the food, and ohmic heating goes directly into the food and uses the resistance in the food. So that's how I read it. Does that make sense to you guys?
Yes.
Oh, good.
Yes.
Good. All right. So that's what I read. So I'll try and reword that question so that it makes more sense. Or maybe I'll just drop it out of the quiz and write it a whole nother one. Just a reminder, if you happen to be in Southern California in February or planning to, February 18th, there's a joint meeting of the RCA, the local RCA, and the SCIFs. This is the only time in Southern California that we meet, that RCA meets. And so it's going to be at Village Green Foods. It's always fun. It's always well attended. So, and I don't know if you guys know Jenny Rossoff, but she's owns Village Green Foods. She does a lot of cook chill. Um, and she does, what do you call that? Proprietary, where people come to her and she makes their stuff, right? So, all right. So these are our learning objectives. So let's talk. I thought I would start by talking a little bit about what is heat. So let me, Alexa, turn off the heater.
I set the thermostat to off.
Yay, I'm overcooking in here. Um, talking about heat, right? So, what is heat? So heat at the molecular level, at the atom level, where we're talking about atoms and molecules, heat is the motion of those molecules. So when we touch something, what we feel as heat is the motion of those molecules. And the faster they move, the more they bump into each other, and the more they rotate around themselves and each other. That friction is what makes makes heat, and that the rotational and vibrational creates friction, and that's what we feel as heat, right? In solids, the molecules are very close together. So let's talk about water, for instance, right? So as a solid, the atoms of the water molecules are very close together, and they don't move very much, right? So and it's mostly conduction from one to the other, right? In a liquid, the molecules are moving faster. You get more movement. They're they're farther apart. And in a gas, they're even farther apart than that. And so you can get a lot of rotational movement. So that's what we're feeling as heat is that. So we can add heat to something and make things go faster. We can't add cold, right? So cold is a reduction in that movement. So what we're doing with cold is removing the heat so that the molecules are going slower. Questions about that?
No.
No? Okay. Thanks, Brian. So is that a new concept to you guys, or do you guys talk about that in your undergrad and in your work life?
No, for myself, I've not been exposed to it. No, this is the
Oh.
first time.
Oh, good. Yay, something new. All right.
I mean, some of it is,
Yeah,
some
yeah.
of it isn't.
Yeah,
Kind of
briefly.
50-50 there.
Yeah. Okay. Good. All righty. Well, it's just a way of thinking about that. So, I always think it's a good idea to have a basic understanding of what's happening, right? So temperature is that's what we call the hotness or coldness, right? Is temperature. So another definition is thermal conductivity is how well this heat transfers. Like something like glass has low thermal conductivity, and and metal has a higher one. How quickly it transfers the heat. So how we measure heat is what we measure it using the term a calorie. So the traditional chemistry calorie is the amount of heat necessary to raise 1 gram of water 1 degree Celsius. So if we were in the chemistry lab or in the physics lab, then that's the calorie, right? It's generally written, this is the beginning, first letter of the word, but it's generally written with a small c, calorie. If we're talking about the calories in food, a calorie in food is the amount of energy it takes to raise 1 kilogram of water 1 degree Celsius. And it's generally written like as kcal or cal, or generally written with a large C, though you do find it other ways, but generally it's written with a large C. And it is, a gram is 1,000 times bigger. A kilogram is 1,000 times bigger than a gram. So it's 1,000 times bigger. So that's how we measure the calories in food. And in fact, when we measure the calories in food, one way to do that is to put it in what's called a bomb calorimeter, which is a kind of a metal box sort of thing. And you put it inside here, and you light it on fire and you burn it up, and you measure how much heat the food gives off. And that's how they measure, the calories in food. Another way to do that is to do a calculation where you look at the carbohydrates, lipids, and proteins, and you can calculate the calorie that way. But this is the most accurate way. So then they measure the heat that's given off. So what they're measuring is the amount of energy, and that energy is measured in calories. Just like distance is measured in inches or feet or kilometers, heat is measured in calories. So technically speaking, a food does not have calories, right? The amount of energy in that food is measured as calories. But that's not how we use it. But anyway. Questions?
No.
No? Okay. All good, Trevor? Yeah, okay, great. All righty. So a joule, the other ways to measure energy, other units of measure, in the metric system, they use what's called a joule. And in a joule, 1 calorie is 4.18 joules. We don't use joules here. Almost everybody uses calories. And if we're measuring the heat for a pound of water, then we use a BTU, or a British thermal unit. And that's a pound of water, 1 degree Fahrenheit. And that's typically used for equipment, right? Cooking equipment like gas ranges and stuff like that, right? Right? Okay. So, but for us, a calorie, that's what we use. So there are two common temperature scales that we use. We don't use Kelvin. They use that in the chemistry lab. There's the Celsius scale and the Fahrenheit scale, as I'm sure you know. So if we look at those scales, these ones right here, Celsius and Fahrenheit, I know that you know that in the Celsius, freezing is 0 and boiling is 100. How neat and tidy that is, right? So that means that there are 100 gradations along here, right? In the Fahrenheit scale, freezing is 32 and boiling is 212. So there are 180 gradations. So we have to take that difference into account when we make the conversions. The other thing is we add the 32 because Fahrenheit, or subtract 32 because Fahrenheit starts at 32 and Celsius starts at 0. Right?
Okay.
So that's why. And so 180 over 100, if we just look at the gradations, is 1.8, which is 9/5. So I kind of thought, I'm not a great math person, but I thought it helped to figure out how they came up with this formula that we have to memorize, right? So does that make sense?
Mm-hmm.
So we can think about the fact that since there's 180 gradations in Fahrenheit, and only 100 in Celsius, that, that there was more of a difference, right? So from Celsius to Fahrenheit, we're going to have to use 9/5 because there's more gradations. And from Fahrenheit to Celsius, we're going to use less, smaller. So it's going to use 5/9 because there's fewer gradations. Yes? You probably have this all memorized. And besides, you just ask Siri and she'll tell you. But there's likely to be a conversion question on the exam. So you want to be able to do this, right? You want to be able to make this conversion. And I always get the 5/9 and the 9/5 mixed up, right? And the subtracting and adding the 32. So knowing where those numbers come from, I think can help remember, kind of. Do you guys have any clues for how you remember the formulas?
No, I don't think I've done it by hand since high school.
Yeah. Same here.
I usually just ask Google or
Yeah,
Siri.
Right. So do I. So, but you should be able to do this, right, in your head. Because cannot take a Google into the exam, and you cannot take a calculator into the exam either. Okay. So you need to be able to do it for yourself.
Something
Any
to work on.
Something to work on, right? Takes a bit of practice, right? So anyway, but I think that it helps to recognize the difference between the two, being that Fahrenheit has 180 gradations and Celsius only has 100. So
That might be a great chef tattoo somewhere on you that you can
As reference.
take into the exam.
like the kids do, right? Right all over your hands. In the old days, what they used to do when you took an exam, right? Question, right all over your hands. Okay. Well, anyway, think about that for a while and let me know if you have any questions about it. To me, it kind of makes sense, but you still have to memorize the formulas, but at least you should be able to look at the answer, right? So if you're going from Celsius to Fahrenheit, you know you're going to have to add 32, right? Because if we're going from here to here, we're going to have to add 32, right? We're going
Correct.
to have to add this right here. And if we're going from Fahrenheit to Celsius, we're going to have to subtract 32, right?
Mhm.
Right, because this one starts at 32 and this one starts at
That's
0.
a zero.
Right. So to go from Fahrenheit to Celsius, we know we're going to have to subtract 32. Right. And then we know that there's more gradations here. So we want to make the number smaller to get to Fahrenheit. And there's fewer gradations here. So we want to get it bigger. Because Fahrenheit's going to be a bigger, higher number. All right. Before I get myself into trouble, I'm going to leave that unless anybody has any question. All right. Just a couple of things from the food code. So this is the food code from 2022. There is an addendum for 24, but I didn't have a chance to go through it. But when we look at the food code, there are some specific instructions about measuring the temperature of food. And one is that devices cannot be constructed of glass unless that glass is enrobed in plastic of some sort, right? So you can't use a glass one unless it's protected, obviously, because you don't want to get glass in your food. So that's one. Also, the Celsius and Fahrenheit shall be accurate to plus or minus 1 degree centigrade. And if you're just using a Fahrenheit, plus or minus 2 degrees Fahrenheit. So that's the definitions for the accuracy of the temperature measuring device. And for ambient air, easily readable plus or minus 1.5 degrees centigrade. So, or Fahrenheit plus or minus 3 degrees. Right. So we know that Celsius has the smaller numbers and Fahrenheit has bigger numbers. So that's what the food code says about temperature measuring devices. You've probably seen that before.
Mhm.
The rate of heat transfer, right? So especially Brian, you did a lot of food safety stuff, right? So did you guys work on that?
No, we did not.
Oh, okay. Well, there you go. There. So the driving force but probably when you buy stuff, it already has that in it, but it's good to know. So the driving force of heat transfer is the difference. So if I'm doing cook chill and I put my bag of food in the ice, right? At the beginning, it's going to start cooling down really, really, really fast. And as I get closer to where they're both at the same temperature, it's going to slow down because the driving force is the difference. So when there's a big difference between your product and the ice water, it's going to cool really, really fast. But as you get closer and closer to the end point, it's going to cool slower. And so the driving force is the temperature difference. Other things that'll affect the heat transfer or cooling or heating for that matter, but cooling is the properties, the rheological properties. In other words, viscosity, flow, thickness, all of those. The thicker it is, it goes back to this principle that we talked about here before. Up here, the thicker it is, the closer the molecules are together, the slower the heat transfer. The thinner the product, the farther the molecules are apart, the faster the heat transfer. The surface area of the pieces, obviously, smaller pieces heat faster than bigger pieces, right? And the thermal properties of the container. So if it's an aluminum can or a metal can, then it's going to be the container is going to heat up really, really fast. So these are all of the considerations that go into effect when we look at heat transfer rates, whether we're talking about heating or cooling. Do you guys have any other examples? My example is always cook chill, but other things that you work with?
Not at the moment. We don't deal with any type of, we have, I mean, we're blenders, we're dry blending ingredients. So really we're not coming across any of this as far as cooking, cooling, chilling, things of that nature.
Okay.
But, it brings me back to kitchen days, cooling down stocks, sauces, things of that nature,
Mhm.
following the time parameters, so on and so forth.
Right. Which is why the time parameter is so long, because when you first look at it, you think, oh, this is going to cool off really fast, right? Which is also why the food safety regulations talk about the size of the container, rather than you put a big stock pot in there, it takes really long time for everything to cool, right? Or whether you put it in a hotel pan or a thinner pan or container, it's going to cool faster because there's going to be, it's thinner.
You're increasing the surface area.
Increasing the surface area, not only of the pieces, but also the product itself, right? Takes less time to get to the center. And that's why the food safety regulations are like that.
I do a lot of work with um, designing food for heating and cooling for specific parameters that clients want. So, like, I've done some food for, we'll just say a coffee company, and they want sub 2 minute ticket times, and they're using a specific type of oven. So we have to engineer that food and get it to heat to a specific temperature in under 2 minutes for them, and we have to prototype enough that we're either using Mary Chef or Turbo Chef ovens. So we have to calibrate for the based on the food we design from a frozen state, we have to calibrate for the amount of convection time, for the amount of microwave time, and once we dial that in, we have to get it under 2 minutes. So we have to log all that data and present it to the client. And same thing with like blast chilling after co-manufacture, we do a lot of data for that too. So I have my laptop in the kitchen a lot.
And so other than these things that I've listed here, what other kind of considerations do you have? I guess if you were using partially microwave, then that is that
Yeah, like Turbo Chefs and Mary Chefs. I mean, you have to really if you're using too much convection and not enough microwave, then you'll end up with a nice crispy outside or a burnt outside and an ice cube inside, and vice versa. You might overheat the inside and it might blow up and not get enough crispness on the outside. So it just depends what you're doing, and and that's why they all have individual settings, because you can program those settings into the oven. But you might be doing a chicken sandwich that's this big, and the next thing might be a small pastry. So everything has to have its own setting.
Yeah.
And at least where I work, and we're responsible for collecting that data. So, and you might, as we're testing stuff, you might throw 30 things away. We'll do a chicken sandwich in there, and if it doesn't work, we throw it away and do another one, throw it away, do another one, throw it away, do another one till we nail it. So
So you work more with the settings on the oven and less with what's inside the food.
no, I do both. Our thing is we have to design the food up front with what our best guess is how it's going to work in the oven. So sometimes we'll go to the oven and we'll do 30 trials, and then we have to re-engineer the food. It just yeah, well, if the client's not happy, and they're paying me by the hour, I don't really care. I'll make it again, but that's just trial and error with new food that's going on. So
Well, cool. Yeah, I didn't think about it that way, but sure. I've never had any experience with those kind of ovens, so I've certainly seen them though.
they're fun. I wish I could have one at home, but they're 20 grand each.
Oh yeah. Oh my gosh, really? Oh wow.
Yeah, 15, 20 grand. Yeah.
Wow. Okay. So, all right. So, thanks for sharing, Ryan. That's nice. That's good to know. So, the one of the learning objectives is to describe the principles of heat transfer, including conduction, convection, induction, and radiation. Do you guys have any questions about these? I'm pretty sure this is something you're very familiar with, right?
Yeah. Yes.
Yeah, conduction, they're banging against each other. Convection, they're moving around. Radiation is heat like from the broiler. So I did want to expand on this just a little bit. So when in food science, we talk about retorting and we talk about the math involved with retorting. But also one of the things that we're talking about with retorting, and actually what Ryan and I are talking about a little bit too, is heat transfer, right? So when they actually calculate for uh, canning, we think about how liquidy, how liquid it is. So are we getting any convection in the can, right? Is that heating at the bottom and rising and going around? If you look at some of the retorts, they rotate and rotate the food in order to get that convection. So the thinner the food is, the faster the heat transfer is going to be. The thicker the food is, the slower the heat transfer is going to be. And there's usually in the food a cold spot, and it's usually, I've been told, down just a little bit lower than it's marked on here, so that it's kind of in the bottom. So if the food is really thick, how long is it going to take that heat through conduction without any convection? For that heat is going to be very slow to get through, which is why they use the great big also they're very energy efficient, but the when they make dog food, for instance, like solid on the inside, right? Or Spam or something like that, they use those big tall things. You ever been to Denver and you go by the dog food place, right? That big hydrostatic um retorts. So they're using pressure, and because it takes so long, they're adjusting it based on how long it takes for the cans to go up and down. So, but the rheology of what's inside the can is going to make a difference, right? Also, the size of the pieces, the number of pieces, and so how fast does the heat get into the liquid and then into the pieces, right? Another thing that we think about in canning is that's really important is this headspace. Because if you have a bubble that's going to circulate around inside of there, that's going to help with convection as well. If the can has a bubble in it a little bit from the outside. So we talk about some of this when we talk about retorting, but I think, with all of this has to be. And Ryan is talking about trial and error. And that's exactly if there's a new food product, at least my experience with canning, which was pretty small and was 40 years ago, but I don't think it's changed that much, is a lot of trial and error. They put a probe into the bottom here and they measure this internal temperature. And then, in trial and error, how long it's going to take to get that to the right temperature for the right length of time. Questions or anything anybody wants to add to that? So there's different kinds of heating. Microwave heating, as you probably know, is electromagnetic. In other words, it's a electromagnetic wave, like a radio wave, or like and those radio waves, depending on the distance this way, determines, how fast they are and what they do. So that's electromagnetic radiation. And so what it does is, if we look at this water molecule from food science, right? Water molecules have positive and negative sides. And so what does that wave do? It causes it to changes the polarization. It causes it to twist. And that twisting is that friction, and that friction is is the heat. So it's the magnetic wave causes the water molecule to switch back and forth, and that makes heat. Make sense?
Yeah.
Yeah. So it's the water. That's why you can't really, heating bread is always difficult, right? Or meat, they don't do well in the microwave. No water, little water. The food code talks about microwave cooking, and it says that it recommends that the food is rotated or stirred midway through, because obviously there are always hot spots and cold spots in the food, so that it's covered to retain the moisture so that it doesn't evaporate. The internal temperature of 165, and allowed to stand covered for 2 minutes. And so the object of that is that once you get these guys twisting, what we want to do is we want to get a consistent heat across the whole thing. So should you ever be involved with writing and directions for things that are microwaved, you have to allow for a standing time so that the heat will even out across the food, right? That's written into the food code.
Interesting.
The cavities and door seals of microwave should be cleaned every 24 hours. Sure, that happens every time, right? Every facility, all the time, every facility, right? So, but the way you know if you've got a good seal is to run your hand around the outside. And if your hand gets warm, then your seal is broken. You can microwave your hand on the outside, right? So, but if you could run your hand around the outside, then you'll know that you have a clean seal and it's all fine. So, I remember, because I'm very old, I remember when they introduced microwave ovens and people were worried that they were going to get microwaved, right? Everybody was worried about microwaves. Not true. So
Hey, Jill,
yeah.
do you remember? I remember microwaves coming out too, and my grandma and grandpa were the first to have one, and all the hubbub and rumors
Yeah.
back then were of old ladies putting their poodles in the microwave after a bath to dry them. Remember that?
Yes. I remember when we got our first microwave, I told my husband, you cannot put a whole egg in the microwave. He says, oh, sure you can. You can cook an egg in the shell in the microwave. I said, you go for it, but you're cleaning it. And of course
Yeah.
because it's heating from the inside out, right? And it expanded and whoo. And my husband said, oh. But I remember the very first microwaves. My dad had a fast food restaurant and he used a microwave oven. It was kind of like a Denny's, a display cooking sort of fast food. And he had a microwave. That was the very first microwave I ever saw. That was pretty cool in the restaurant. So, but just as I was talking about before, the difference in frequency. So ionizing radiation is, X-rays and gamma rays are way up here, really short. And radio waves are way down here, really long. And microwaves are right in there. And visible light is in between, right? So it's the distance of the tips that makes the difference. And what happens is that wave goes through and causes the water to flip and to oscillate and to make for heat. So we spend a lot of time in food science talking about water, right? So here it is again, right? So same principle, positive one side, negative on the other side. Induction cooking. It's the direct induction of heat into the cooking vessels, into the cooking vessel, and then the vessel cooks the food so that the heat itself the element itself is not hot. It just uses the waves to heat the bottom of the food. The substance, this is a good vocabulary word, might show up on a quiz. I should put this question on the quiz. Ferromagnetic, that means a substance that'll react to the waves. That's what's called a metal, right? So you guys all know about induction cooktops. They're like super fun, super fast. They heat up really fast and they cool down really fast. So
Yep.
hard to get used to. You can use anything but glass, right? Pretty much. Or
They are hard to get used to.
yes. I didn't have a range for a while. My range broke and I have one. I'm going, oh, I'll never get used to this. Ohmic heating uses the same sort of principle, but instead of heating the pan, this is where we started in talking about, it heats the food on the inside. So particles suspended, especially weak salt containing solutions, right? So it causes the electrical current passes through the food and causes the rotation, the heating. So does anybody have anything to do with ohmic heating? I don't know that it's used.
No, until I did the reading, I'd never heard of it.
Yeah. I think it's one of those new techniques that hasn't really caught on, right? But if you did something in a pouch, for instance, it might be a really good thing. You could pack it up in the pouch and heat it. It says good for soup, sauces, stews, salsa, fruit in syrup, milk, heat-sensitive liquids, soy milk. I guess because you don't overheat them. Rapid heating, less.
But it's not yet approved by the FDA. You got to love that.
Not yet approved.
Yeah, I think it gets used more overseas than it does here. I
Okay.
think it's just going through trials here.
Okay. Yeah, it's probably expensive and
I'm sure it is.
yeah. So irradiation, food irradiation isn't not done a lot here in the United States because I don't know, people are worried that their food's gonna glow in the dark or something. But the nice thing about food irradiation is that it's a cold process. And the way it's done is they don't use not like it's not like generating an electricity generating plant, but what they use is the rods from those kind of I think the kind of spent ones that are giving off the beam. So again, we're talking about this radio wave. So what happens is, and there's a facility in Irvine, I think it's still there anyway, and that does irradiation. They don't do much food. They do spices, irradiated spices, but they don't do much food. There was a plant to do chicken in Florida, but I don't know that it ever got off the ground. That was a long time ago. But essentially, what happens is you package your food, and so if you can sterilize what's inside by not heating the food, then it makes it really sterile on the inside. And so the way it's done is that the food runs along a track, and the track goes in and then goes around like this, and it goes around these rods and then back out again. And so the rods when they're not in use, are kept in the water, and then the rods rise up, and then you control how much radiation the food or the item is getting based on how fast the track runs. So it works really, really, really well. It's a cold process. And this whole big shell is a big old cement block. But the radiation beams cannot go around the corner. So it has, lots of corners so that the beams can't get out. So it's really cool. I got to go in there and walk around, look at it. That was pretty cool. But other than spices, I don't know that much is being irradiated in the United States because I don't know, people worry about such things as that, right? But it's safe. Mostly, I think what this facility does is medical supplies, right? So things that used in, single-use things like in operating rooms and things like that, medical supplies. But I'm sure, do you guys use irradiated spices?
No.
Yeah, absolutely. I have clients who won't do any seasoning work unless you can prove that what you're using is irradiated. It
Yeah,
just depends on the client, but
right.
a lot of them ask for irradiated spices now because
Yeah.
it's just another thing that they don't have to worry about as far as liability.
Right.
They can
Yeah.
pass it on.
Yeah.
Mhm.
Right. And not only that, spices themselves are dirty, really dirty. So
Especially when you look at organics.
yes,
We bring
especially
in a lot of organic product, and it's pretty amazing what you find in some of these boxes and bags.
yeah. Well,
I mean, it really is. I mean,
Yeah.
we're certified organic in one of our plants, and a couple of years ago, I had an infestation problem, and after a couple of weeks of searching and searching and searching, we found the issue, and it was in organic material.
yeah,
So in talking with QAI, organic body, it's, you guys help me. You don't want to treat it in the fields, but then you send it to me. But then when I have it in my plant, you won't allow me to use X, Y, and Z to control it, to control any infestations or anything of that nature. I've gone through a lot of trials and tribulations with my pest control company and to build a case. And finally we got through it, but it's amazing what you find in the organic ingredients.
yeah,
And just dealing with that is pretty crazy.
right. And we're not even talking about bugs here, but bacterias, for instance, so if you can control how clean the product is when you start the process, then then your output is going to also be cleaner. So, and I'm sure all those organic things, and even though people say I want everything organic, they probably don't want a bug or whatever in their food. So it's an interesting
I
process.
do a lot of work with bugs in food right now, especially crickets. Cricket powder.
Oh, yeah.
Really? Huh.
Yeah, as a protein. We're working on a line of sauces that is protein enhanced with cricket powder right now, and
Wow.
huge in other countries. It is not big
Mhm.
here yet, but
Where are you pulling your cricket powder from? Like, where do you order your
uh,
cricket powder?
um, I can't really say.
But overseas, I assume.
Oh yeah, overseas.
Okay.
Yeah, like we did a cricket mole sauce for a company in Mexico. Um, and it was probably the best mole I've ever tasted in my life.
Now, is this cost efficient?
Yeah, yeah.
Mhm.
Depending on what, on what opportunity space they're developing for, but yeah. I mean, is it going to be on the shelf at Walmart? No, but
No, no. Interesting.
Huh.
yeah, it is really interesting, and it's only getting bigger. And
I've seen people talk about that.
yeah,
So,
crickets and grasshoppers are
Well,
huge.
there's a huge protein craze going on right now, so you're going to see more of that.
Yeah,
yeah, yeah, yeah, probably true. Right. And I think that things like, the impossible meats and all of those kinds of those things are losing favor because now people are talking about using whole foods and not, and they're so highly processed. So
yeah.
so using for crickets are natural, right? So organic, probably.
They are
Probably
of
have a
the
nutty
earth,
flavor.
yes. They really don't impart a flavor, which is why I think they're so popular for, like I forget what the like the compared to whey protein, they're like, I want to say 4 or 5 times more protein potent, and your body absorbs it even better. I have sheets of data on it, but um,
Is it gluten free?
yeah.
I would assume.
Oh yeah,
Oh yeah.
it's 100% protein. I mean, it's think of it like a lobster shell or a crab shell or a
Yeah.
crawfish shell. Like it's an exoskeleton. It's 100% protein, and it's really easy to dry those things out and pulverize them. Like so,
I'm gonna have to look into it for sure.
yeah, it's worth Googling. It's you can go down the rabbit hole for sure.
No, I want to get a sample and play with it for sure.
I'll let me work on that. Send me your address. Maybe I can send you a sample.
You got it.
Yeah,
You can do that through the inbox
yeah.
in Canvas. So then just want to talk just a little bit about high pressure processing, which has really been a boon for the avocado industry, right? That's where I first saw it anyway. They are using it for things, but essentially what you do is you put your food inside of a pouch, you put the pouch inside of a great big container, and you add water and then increase the pressure. And it's the pressure that kills the bacteria that are in there and also makes the guacamole, right? So it squishes the avocados and makes it really fresh. The originally they didn't put any additives in there, but now they're using a slight acid to keep it from the enzymatic browning from happening. So high pressure processing, I understand they can't keep up with the demand. So definitely something that's happening. And so if you go to the supermarket and you see the guacamole in the little packages,
That's
right?
how it's made.
That's how it's made, high pressure processing.
Interesting.
Yeah, it's really interesting. Makes for really good guacamole. And you don't have to add it, it's airtight. You don't have to add a lot of additives or you don't have to acidify it or anything like that too
No,
much.
I use it a lot back in the days in large catering events and functions of that nature. It came in handy, that's for sure.
Yeah, yeah, yeah. So they
When
can
somebody wanted guacamole for 2,000 people.
right. Yeah. So so high pressure processing uses hydrostatic. So if you look at that word, in case you don't know what it means, hydro always means water. So hydrostatic pressure of 87,000 pounds per square inch. That's impressive.
That is impressive.
Yeah.
Wow.
So, the kitchen equipment, I put this in here because one of the students who wasn't a culinary student had questions about the knives. Do you have any questions about knives or ladles or scoops or any of that? Should be
No.
No?
Nope, fine with all of that, right? You should definitely know these. So, any questions or comments about anything? That's all I have, and we're almost out of time. Look at that, I'm right on time.
Yeah.
Yes, Jill. Good
No,
job.
not at the moment. Some research on my end, to familiarize myself with a few things. But no,
All right, let me stop the recording someplace. Someplace. Oh, hell. Excuse me. I don't know what I did. Oh, there it is. They move everything. It's their fault.